This is a short audio tutorial on the properties of light. And the properties of light we're going to describe in this tutorial actually have to do with our introduction to quantum mechanics.
We're going to start a unit on quantum mechanics. This is a topic that many people find very daunting. We do it in general chemistry, and we do it early in general chemistry, because quantum mechanical principles explain a huge amount of what we see in the laboratory and in the environment. In fact, quantum mechanical theory applies everywhere. For large objects, whether we're talking about your mouse, your body, or the sun, quantum behavior averages out, and as a result, we don't really see it. Sir Isaac Newton, the founder of Newtonian physics, couldn't account for quantum mechanics because he was studying large objects. Once we start looking at nanomaterials, the objects are small enough to start to exhibit quantum behavior. What are we talking about when we talk about nanomaterials? Typically, we're talking about materials where the particle size is made up of anywhere between dozens to thousands of atoms. And this is a small enough amount of material that macroscopic particles no longer apply. Albert Einstein was famously not a fan of quantum mechanics. He was unhappy with the statistical nature of the theory, and he famously said, "God does not play dice." There's a very classic probability statement having to do with 100 monkeys, 100 typewriters, and 100 years. It's a statement of random probability that says if you give 100 monkeys 100 typewriters and wait for 100 years, that eventually they will type out the complete works of Shakespeare. Well, let's talk about quantum mechanics versus normal modes of matter. Before we do that, it's important to understand that when we take experimental observations in the laboratory, we end up with what happens. And the scientific laws that we talk about are our attempt to say what always happens when we step into the laboratory. Theories, on the other hand, are designed to tell us why things happen and provide some sort of framework for how we see the universe. Quantum theory is the why of the really small. We're talking about individual subatomic particles like electrons, individual atoms and small groups of atoms in nanoparticles, or individual packets or particles of energy called photons. Einstein famously mostly worked on cosmic scales, suns, gravity, the expansion of the universe. Currently, a big topic in science revolves around something called quantum computing, which is using quantum mechanical behavior to design computers. These are computers with components that are capable of operating on quantum principles. A normal computer, what we refer to as digital, which means each component in the computer has two settings, on, off, or 0 and 1. A quantum computer element is capable of either being on, off, or simultaneously being on and off. So we, instead of a choice of 0 and 1, we have a choice of 0, 1, or 0 and 1 simultaneously. These computers are currently being built by companies like Intel, Google, and IBM. Interestingly enough, there is a commercial application in many homes right now of quantum mechanics. The most expensive TVs that you can buy generate their colors based on quantum mechanics using materials that are referred to as quantum dots. By the last slide of this presentation, we'll talk about how those quantum dots actually work. We're going to start out talking about light and slowly work our way into matter. Light, or what we would think about invisible light, is a convenient but imprecise term. Light is defined by what our biological system is sensitive to, and it's basically an accident of evolution. Other organisms can see deeper into the blue than we can. Other organisms can see farther into the red than we can. Overall, we talk about electromagnetic radiation being a better term. This includes not just visible light, but things like X-rays, microwaves, radio waves, infrared light, etc. We talk about the speed of light being constant, but we need to be careful. The speed of light is constant in any single environment, but is different in different media. The speed of light that we normally use when we're doing calculations is the speed of light in a vacuum. The denser the material, the slower light progresses through the medium. We'll use terms like amplitude, frequency, and wavelength as we are describing electromagnetic radiation. The interaction of electromagnetic radiation and matter is ultimately a transfer of energy, either light being absorbed by matter and the energy represented by that light being absorbed by the matter, or matter spontaneously producing light, losing energy and producing light as a photon. I insist for my general chemistry classes that energy is the reason for everything, no matter what we're studying, and we'll see how that works as we go through these materials. All right, so the nature of light. Is light a wave or a particle? Or is it both? We will end up describing light as both a wave and a particle, and that's what we refer to as duality, where something has dual characteristics. Electromagnetic radiation is best described as the propagation of perpendicular oscillating electric and magnetic fields, where we have the direction the light is heading in, and then in the two other axes, the x-axis and the y-axis. In one axis we have an electric field, in the other axis we have a magnetic field. We'll talk about variables where nu is the frequency. I'm sorry, I have two different looking symbols here for nu. Nu is the frequency of light, lambda is the wavelength of light, and of course in the above equation c is the speed of light. We'll use all of those variables in our calculations in this module. Well, when we talk about the electromagnetic spectrum, what we're talking about is a huge variation in the energy represented by different wavelengths of light. So if we study the diagram that's shown on this slide, you can see we're going to work all the way from X-rays up through UV, visible light, infrared, microwaves, radio waves, TV waves, and ultimately power and telephone transmission. We will label one end as low energy, the other end as high energy. On the high energy side, you can see X-rays and gamma rays, visible light, working all the way down towards lower energy. If we take a look at the characteristics of the electromagnetic radiation in the spectrum, in the X-ray region, we talk about ionizing radiation because the photons in the X-ray range are capable of actually breaking bonds in the compounds that we're interested in. In UV visible, we talk about electronic spectra as matter absorbs visible or UV light. We've got electrons that are transitioning back and forth between various electron orbitals inside of the atom or molecule. More about that later. In the infrared range, absorbing a photon causes a molecule to vibrate, but electrons do not change orbitals. In the microwave region, we call that rotational spectra, where the absorbance of microwave energy causes molecules to rotate. That's how the microwaves in your kitchen work. Those microwaves are tuned to the rotational energy of water molecules. And it's one of the reasons that if you put something in a microwave with no water in it, say a ceramic plate, it heats up very slowly at best. Where if you put in food that has a high water content, the friction from the rotation of those water molecules heats up that material quite quickly. In the radio and TV range, we have things like NMR, if you're a chemist, or if you've ever had a broken bone or torn ACL in a hospital, they'll take an MRI. An MRI is the same thing as NMR. NMR stands for nuclear magnetic resonance. When that technology was converted into healthcare, people were afraid that the term nuclear would be associated with bad radiation, so they renamed it to take the nuclear term out. But we're probing your body with radio waves as we take an MRI to see if you've got soft tissue damage. You'll often see this plot flip from left to right, depending on whether you're talking to a physicist or a chemist. This particular diagram with high energy on the left is a representation most often associated with physics. Chemists, especially spectroscopists, will flip this diagram so that high energy is on the left and low energy is on the right. We will see examples of that in slides farther in the presentation. When we're talking about white light, sunlight, other sources of white light, we're often talking about something called a broadband emitter. This is a famous quote out of one of Isaac Newton's scientific treatise, Optics, published in 1704. And he said, "Do not all fixed bodies, when heated beyond a certain degree, emit light and shine? And is not this emission performed by the vibrating motion of its parts?" Well, Isaac Newton made this statement very early in the scientific revolution, obviously. And he did not have models of atoms and protons and electrons, but what he had was a simple observation from a blacksmith shop. If you heat a piece of iron up hot enough, it will glow and emit light, emit photons of certain energies. Now we refer to this as Planck's black body radiation, and the simple statement of Planck's black body radiation says that every object emits photons, and the energy of those photons correspond to its temperature. This is exactly how night vision goggles work. You might be surprised to know that your body right now is busy emitting photons. Your body is emitting photons in the infrared range, which your eyes are not sensitive to. But of course, we can make devices that are capable of seeing and analyzing those photons. That's where we get our night vision goggles from. The only way that your body stops emitting photons is if we cool you down to absolute zero. That's 0 degrees Kelvin, and then no photons come out. We often perceive infrared photons as heat because the vibrations caused by those photons when they hit our body causes a vibration of molecules, and we end up with heat induced by friction. If we take a look at how Planck's black body radiation process plays out, we will see here on the x-axis we've got wavelength. So if we have wavelength on the x-axis from low to high, we've got energy in the opposite direction. That means high energy is to the left in this graph, low energy is to the right. We've got 4 different traces here of objects at different temperatures. 3,000 degrees Kelvin, we are mostly emitting our photons above 1,000 nanometers or 1 micron, where our eyes are not sensitive. We would perceive those as infrared photons. As we go to 4, 5, 6,000 degrees Kelvin for the temperature of our object, the energy of the photons shifts to the left, higher energy photons, lower wavelength. And ultimately, for an object that's at 6,000 Kelvin, it's emitting the vast majority of its photons in the visible region, where our biology is capable of perceiving them. So I'm going to ask you a quick question. I do not want you to think about this. I want you to just react to it. Which is hotter, something that's red hot or something that's white hot? Well, somehow you instinctively know the answer to that. Something that's red hot, that's emitting most of its photons in the red spectral range, is cooler than something that's white hot, where the temperature of that object has shifted, and the object is emitting photons in the entire visible range, including down in the blue range. Well, we have different light sources in the laboratory and in the environment, and we talk about the difference between broadband radiation versus quantized radiation. Quantized will be an important vocabulary word. And if we take a look at the relative energy produced by a variety of different light sources, we see the following behavior. Again, we've got wavelength on the bottom, low wavelength to the left, high wavelength to the right. Energy is the reverse of wavelength. So we've got high energy on the left, low energy on the right. And we have a variety of different light sources. We have the sunlight at noon. We have your standard tungsten bulb. We have LEDs. We have barcode readers. We have mercury vapor lamps, which are the fluorescent lamps that we have in many fixtures. Well, the sun is very hot and acts as a broad body black body radiator, and because of its temperature, emits photons across the entire visible wavelength range. When our eyes get hit with all these wavelengths simultaneously, we perceive that as white. Incandescent bulbs, which are the standard light bulbs invented by Thomas Edison, are also broadband black body radiators. Actually produce most of their energy in the infrared, and we perceive that as heat. Of course, that's why when you touch an incandescent light bulb that's been on for a while, you're likely to burn your hand. And it's one of the reasons that we're interested in replacing tungsten light bulbs from an energy efficiency point of view. Most of the energy we put into a tungsten light bulb does not produce visible light, it produces heat. If we make a lamp out of atomic vapors like mercury lamps, and that's the source of most of the fluorescent lamps that we have, we get very sharp lines that represent specific orbital transitions in mercury vapor atoms. We also get little to no heat from these lamps. As you can see, when we get out towards the red area of the spectrum leading towards infrared, we have very little energy output in that range from these fluorescent light bulbs. We also have a couple of other very interesting light sources. We have a light source that works by light amplification, by stimulated emission of radiation, and of course that's a laser. Lasers work based on an entirely different set of physics and typically produce very narrow lines that have to do with the solid state structure or gas structure of those lasers. So we don't have broadband emission now, we've got quantized emission. We have photons coming out with only a certain quantized or fixed value of emission and nothing else. We've got the same situation with semiconductor LEDs. Most of your phone displays and computer displays are working based on light-emitting diodes. Well, I'd like to draw back to an experiment hopefully you got to observe from high school physics or maybe from a college physics class, and that's called diffraction. If we take a look at an experiment conducted, again, very early in the scientific revolution, Thomas Young, in the first year of the 19th century, demonstrated that light, in fact, has wave properties using the following experiment. He started out with a light source. Doesn't really matter what it is. I've got an icon for an incandescent light bulb here. And I'm going to show progressive waves of light receding away from this light source. A little ways away from the light source, we're going to put a barrier that has two slits in it. And the light waves coming off that light source will exit that barrier through two holes. And now what I've got is I have the source of two different waves. And if I put a white screen past that barrier, what I will see is I will see a pattern of light and dark bars that correspond to the distance away from that barrier and the distance between the two slots in that barrier. Well, if we analyze the wave properties of light and see what's responsible for the light and dark areas, On parts of those screens, we have the waves from the two slits lining up so that the maximum amplitude of those waves actually is in exactly the same position. When those get added together, we end up with a wave of a much higher amplitude, giving us those very intense white lines. This is referred to as constructive interference. There are other areas on that screen, however, where the two waves that are resulting from those two slits are exactly half a wavelength out of position. And the peak in one wave slit corresponds to the trough in the other wave, and when we numerically add those together, we end up with 0. So we have no light and a dark area on the screen, and this is referred to as deconstructive interference. When I was in high school many years ago, in physics, we actually had what are referred to as wave tables, where we could model this behavior using waves in a water pool, and show you get exactly this behavior, this wave behavior of constructive and destructive interference using water. If you are in the right spot in a beach, where you have two waves coming in from different points, you can actually see constructive and destructive interference for those waves on the beach, which is kind of interesting. So this experiment proves that light has wave properties. But of course, the funny thing about quantum mechanics is that we have to be able to simultaneously hold in our minds contradictory evidence. And we'll find that we can run experiments that also show that light, as opposed to being a wave, has particle properties. The particle property experiment we typically talk about is referred to as the photoelectric effect, and shows that light has particle properties as well as wave properties. And what we find is light of sufficient energy can eject electrons from some metals and semiconductors, producing an electrical current. And this electrical current is referred to as a photocurrent, so photons or light particles producing an electrical current. And we can even write an equation for how this works. The energy of our individual photons equals h times nu, where h is something called Planck's constant, that has units of joules times seconds, and we can either state this as Planck's constant times frequency. Frequency has units of 1 over seconds. Joules times seconds times 1 over seconds. Seconds cancels out, and we end up with units of energy. Or we can write this as Planck's constant times the speed of light divided by the wavelength. Sometimes that formula is more convenient because we're given data that has wavelength units and not frequency units. Einstein explained this behavior by theorizing that light comes in packets called photons with fixed or quantized energy values. So if we assume that light only has wave properties and those wave properties are continuous, we have no way of theorizing why that wave is capable of kicking out an electron. If we assume that light has particle properties, what we essentially are talking about is a billiard ball, where one billiard ball has enough energy to move another billiard ball. Well, it's this photoelectric effect that provides us things like solar cells, digital cameras, night vision goggles, and all sorts of very interesting devices that we take for granted in 21st century living. The electron's energy after it's kicked out of the material can be easily calculated by the following formula. The energy of the incoming photon, Planck's constant, times the frequency, minus what we refer to as the force of the electron binding the energy in the solid. So those electrons don't magically just jump out of that solid. There's a force holding the electrons into the energy into that solid. We refer to that as the binding force. And the energy of the electrons produced in this photocurrent has to equal the energy of the incoming photons minus whatever energy is holding those electrons in the solid. The energy holding the electrons in the solid can be calculated using something called Coulomb's law, which we'll explore in later chapters. Coulomb's law governs the attraction or repulsion of charged particles, and the energy of attraction or repulsion is equal to 1 over a bunch of constants that we won't talk about now, times the charge on the particle of attraction versus the charge on the electron, divided by the distance between the electron and whatever particle is attracting or repelling it. As I will insist for the rest of the year in general chemistry, energy is the reason for everything, and we can use that in our calculations.